So this is a very simple reference table to give designers some idea in terms of the value of the safety factor and what it means from an application point of view. So for instance, anything between a 1.25 and 1.5, so this is more or less relating to material that's exceptionally reliable under controllable conditions. So again, this is something that you need to do. So if the conditions are such that there's, the control of these conditions, okay, is not really absolutely under your control, then the safety factor probably needs to go up a bit. All right, so controllable conditions subject to loads and stresses that can be determined with certainty. So this all comes down to the confidence that you have in the material, the nature of the loading conditions. So as I stated, normally not that critical. And you're also looking at a situation whereby you have a clear idea in terms of the operation environment, and you have more or less absolute control over the operational condition from an environmental perspective. 1.5 to 2. So again, knowing a bit much about the material being used for the fabrication of a given product or component. Reasonable understanding in terms of how consistent the environmental conditions are, and that the measure of the stress and stresses can be determined without issue. 2.0 to 2.5, so again, average materials, some understanding of the operational environment, but again, the loading and stresses can be determined, but these stresses are more or less going to be higher than that of safety factors related to material, whereby there is a good foundation in terms of the knowledge and the reliability of the material. But above that, you're now going to go into materials that if it's kind of new and there isn't that much data regarding the operationability of that particular material, then this is where some consideration of a high safety factor needs to be considered. Or if you have a situation whereby the material is quite brittle and there's very little plastic yield after the yield limit, then this is where you probably need to think about, is it smarter to have a larger safety factor? Again, if there's too much uncertainty in terms of the probability of quick changes in the material, the operational environment of the component that the designer doesn't really have a lot of control of. So let's assume that you've got, let's say, a vehicle, for instance. So a vehicle that you've designed to operate in, let's say, the UK. All right, you've got some understanding in terms of that environment. But what about if that particular vehicle needs to operate somewhere else on the globe, let's say on the African continent, whereby temperatures are higher and much more consistent, or situations whereby you've got frequent fluctuations in terms of the humidity and things like that. So again, these are some of the things that needs to be considered in terms of, okay, what would be a desirable safety factor for components that constitutes that vehicle's assembly. So as designers, you do need to have a good understanding in terms of why you're selecting this safety factor. Why is it reasonable in terms of defining what the ideal design stress needs to be? So something for you guys to think about. Again, the other considerations that probably need to be thought of. So as I more or less inferred, brittle material. So again, because you've got that limited period of uniform plastic deformation, it might be worth thinking about, okay, what will be the best safety factor for a material that's quite brittle, and particularly not having that much substantial material base, particularly if you don't have the facilities in performing additional testing to give you that knowledge base of the material in terms of how it will realistically perform when being subjected to some form of external stimulus. So this is where you need to think about, okay, do you double the safety factor? So the previous page we looked at typical values of 3, but maybe for dynamic loading situation, maybe that needs to be doubled or tripled, depending on the material. again, impact forces. So again, it might be worth maybe thinking about an impact factor or some measure of dynamic magnification factor, because we do know that at the point of impulse, the force within that time period can be considerably high. So what do you do then? So again, these are some of the things you need to think about, because there's always that uncertainty that when you design products from a particular material, when the component is dropped or it collides with a surface or another object, what is that possibility that the material is able to absorb that amount of energy to ensure that it doesn't deform? And you also got, the issue with repeated loading. So I did make mention about fatigue. So again, it's not all materials that have a defined fatigue limit. So again, this is where you probably need to think about, okay, if you design in respect to fatigue, what will be the ideal safety factor for that given component? So these are some of the things that's the design issue we do need to think about when it comes to design and engineering components. So let's look at a simple example. So in the diagram, we've got a bolt and nut. The bolt is being subjected to an external force of 20 kilonewtons. And we've been given some data regarding the material. So the material has a UTS, so that's the ultimate tensile strength limit at 450 MPa. The yield strength is given as 250 MPa. And we've been given a safety factor of 2 based on the fact that the material used for the fabrication of bolt has been utilized over a longer period of time. So there's substantial amount of knowledge regarding the performance and behavior of this particular material. So we've been given 2 design situations to look at. So the first design situation is to calculate what would be the ideal diametric size of the bolt if it were to be designed to deform within its elastic limit. So that's the first challenge. So what would be the minimum bolt size requirement? And the second design situation is to predict what the diametric span of the bolt needs to be if deformation is allowed to occur beyond yield before eventual failure. So one, we're looking at designing to ensure the material behaves within the elastic limit of the given material. So this, we got the information from the material database with respect to ASTM grade A 36 steel. So that's essentially where this material information came from. And this is something that we'll instruct students to do when it comes to your projects or your assignments. Always make it a point to reference your source materials unless it's been given by your instructor. So let's have a go working through this problem together. Let's look at situation 1 and work out the diameter of the bolt. If we assume that deformation is under yield, okay, so we're assuming that deformation is set to elastic limit. Okay, so let's write down the data required. So data required, the yield stress, so sigma y, that's been given at 250 MPa. And we've also been given the safety factor. So the safety factor, or the factor of safety, however you want to call it, that's S subscript F, that's given at 2.0. Since the safety factor needs to be greater than sigma y over sigma d, okay, and we shouldn't forget that sigma d is the design stress. Okay, you can call it the design stress limit. So by making sigma d the subject of this equation, the design stress sigma d will be equal to sigma y over safety factor. Okay, right. That equal, okay. So this will be equal to 250 over 2.0 MPa. And this would give about 125 MPa. So we've worked out the design stress. So we now have the information to work out what the diametric size of the bolt needs to be if we're assuming that the formation needs to be within the elastic limit of the material. So we know that from first principles, okay, stress sigma will be equal to the applied force divided by the area. Okay, so let's call that equation 1. And since the bolt is circular, the area, okay, we're going to use pi squared over 4. Let's call that equation 2. So if we substitute equation 2 into 1, then sigma d will be equal to f over pi squared over 4. So let's simplify three. So sigma d will be equal to 4 f over pi squared. So making d, which is the diameter of bolt, then d will be equal to 4f over pi sigma d square root. So we can now substitute known variables into the equation and work out the diameter of the bolt. We know that F is given as 20 per newton, that's basically 20,000 newtons, and we've calculated sigma d to be 125 MPa, which is 125 times 10 to the power 6 PA. Okay, and don't forget that PA is the same as Newton meter squared. Right. So if we substitute known variables, we'll have 4 times 20 times 10 to the 3 over pi times 125 times 10 to the power of 6. Bring out a handy calculator and do the computation. So we have 4 times 20,000 divided by pi times 125 to the 6. And this will give 2.0372 times 10 to the power 4. The square root of that. Our units would be in meters. That's 0.5. And that would give 0.2 0.0143 meters, which is the same as 14.3 millimeters. So this is the minimum size requirement. But if we're assuming that we're not going to be fabricating this boat, then we need to look for the nearest possible stock size by rounding this number up. If I recall, there isn't a standardized 50mm boat size that you can get off shelf. So the nearest possible metric size boat will be about 16mm. And there we have it.
Alright folks, so hopefully everything makes sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.